Humanity has always gazed at the stars, dreaming of reaching distant worlds and pondering the mysteries that lie beyond our planet. From ancient civilizations mapping the constellations to modern astronomers using powerful telescopes, our fascination with the cosmos has been a constant throughout history. We've always sought to unlock the secrets of the universe, to understand the fundamental forces that govern everything from the smallest particles to the largest galaxies. This quest for knowledge has driven us to develop new technologies and push the boundaries of what we thought possible. But our journey of exploration demands a reliable and long-lasting source of energy. Traditional power sources like solar panels and chemical batteries have their limitations. Solar panels require sunlight, which isn't always available in the depths of space, and chemical batteries eventually run out of power. What if I told you that hidden within the heart of the atom lies the key to powering not just our spacecraft, but our future? This key is the nuclear battery, a technology that promises to revolutionize the way we think about energy. Nuclear batteries, unlike their bulky nuclear reactor cousins, don't rely on fission or fusion. Instead, they harness the energy released by radioactive decay, a process that occurs naturally in certain materials. This means that nuclear batteries can be much smaller and more compact than traditional nuclear reactors, making them ideal for a wide range of applications. Instead, they harness the energy released by radioactive decay. This process involves the transformation of unstable atomic nuclei into more stable ones, releasing energy in the form of radiation. This energy can then be converted into electricity, providing a steady and reliable power source. This makes them compact, reliable, and capable of generating power for decades, even in the harshest environments. Whether it's the freezing temperatures of deep space or the extreme conditions on distant planets, nuclear batteries can keep our devices running smoothly. As we stand on the precipice of a new era of exploration and innovation, nuclear batteries promise to be our constant companions. They offer the potential to power everything from spacecraft and rovers to medical devices and remote sensors, opening up new possibilities for scientific discovery and technological advancement. Imagine a world where pacemakers never need replacing, where medical devices can operate continuously without the need for frequent maintenance or battery changes. Imagine rovers that can roam distant planets for centuries, gathering valuable data and sending it back to Earth without ever needing to recharge. And imagine remote sensors that can operate without interruption, monitoring everything from environmental conditions to structural integrity in the most challenging environments. This is the promise of nuclear batteries, a promise of a future powered by the very building blocks of the universe. By harnessing the energy of radioactive decay, we can create power sources that are not only incredibly efficient, but also remarkably durable. Join me as we delve into the fascinating world of nuclear batteries and explore their potential to revolutionize our world. From powering our most ambitious space missions to transforming everyday technology, nuclear batteries hold the key to a brighter, more energy-efficient future. Our journey into the realm of nuclear batteries begins with the pioneers, the radioisotope thermoelectric generators, or RTGs. These incredible devices have been at the forefront of space exploration, providing a reliable and long-lasting power source for some of humanity's most ambitious missions. From the cold, dark reaches of interstellar space to the rugged terrain of distant planets, RTGs have proven to be indispensable. For decades, RTGs have been the unsung heroes of space exploration, powering missions to the farthest reaches of our solar system. They have enabled us to explore places where solar power is insufficient or unreliable, such as the shadowed craters of the Moon or the distant icy worlds beyond Neptune. Without RTGs, many of our most significant space missions would have been impossible. These workhorses rely on the heat generated by the natural decay of radioactive isotopes like plutonium-238. This heat is then converted into electricity through thermoelectric materials, providing a steady and reliable power source. The use of plutonium-238 is particularly advantageous because of its long half-life, which allows RTGs to function for many years without the need for refueling or maintenance. Think of the intrepid Voyager probes launched in 1977 and still going strong, sending back whispers from interstellar space. These spacecraft have traveled farther than any other human-made objects, and they continue to communicate with us, thanks to the power provided by their RTGs. The Voyagers have given us invaluable data about the outer planets and the boundary of our solar system, all made possible by the reliable energy of RTGs. What keeps their instruments humming and their signals reaching us across billions of miles? You guessed it, RTGs. These power sources have enabled the Voyagers to operate for over 4 decades, far beyond their original mission timelines. The longevity and reliability of RTGs have made them a cornerstone of deep space exploration. They are the steady heartbeat of these distant explorers, providing a lifeline in the cold vacuum of space. Without RTGs, the harsh conditions of space would render many missions unfeasible. The ability to generate power in the absence of sunlight and in extreme temperatures makes RTGs uniquely suited for the challenges of space exploration. Closer to home, the Mars rover Perseverance is busy searching for signs of ancient life, powered by the reliable energy of an RTG. This rover is equipped with a multi-mission radioisotope thermoelectric generator, MMRTG, which provides the necessary power to operate its scientific instruments, drive its motors, and keep its systems warm during the frigid Martian nights. The success of the Perseverance mission is a testament to the critical role that RTGs play in modern space exploration. These robust power sources require minimal maintenance and can operate for decades, making them ideal for long-duration missions where solar panels simply wouldn't cut it. Solar panels, while effective in certain environments, are limited by the availability of sunlight and can be affected by dust, debris, and other factors. RTGs, on the other hand, provide a continuous and reliable power source, regardless of environmental conditions. RTGs have proven their mettle in the most extreme environments, demonstrating the potential of nuclear batteries to power our most ambitious dreams. From the icy moons of Jupiter to the scorching surface of Venus, RTGs have enabled us to explore and understand our solar system in ways that were once thought impossible. As we look to the future, the continued development and use of RTGs will be essential for the success of our most daring space missions. But how do RTGs actually work? To understand this, we need to delve into the fascinating world of thermoelectric phenomena. The secret lies in a fascinating phenomenon known as the Seebeck effect, discovered in 1821 by German physicist Thomas Johann Seebeck. Seebeck's discovery was groundbreaking, revealing that a temperature difference between two dissimilar electrical conductors or semiconductors produces a voltage difference between the two substances. Imagine two different metals joined together at their ends. This junction of metals is where the magic begins. Now heat one end of this junction. As the temperature rises, the heat energy causes the electrons in the metal to gain energy and move more rapidly. What happens? Electrons, those tiny particles that carry electric current, start to flow from the hot side to the cold side. This movement of electrons from the hot end to the cooler end creates an electric current. This flow of electrons, driven by the temperature difference, is what we call electricity. The greater the temperature difference, the more significant the flow of electrons, and thus, the greater the electric current generated. RTGs exploit the Seebeck effect by using the heat generated from radioactive decay to create a temperature gradient across a thermocouple, a device made of two different metals. The heat from the radioactive material is absorbed by one end of the thermocouple, while the other end remains cooler. This temperature difference drives the flow of electrons, generating a steady stream of electricity. The continuous decay of the radioactive material ensures a constant heat source, making the RTG a reliable power generator. The beauty of the Seebeck effect lies in its simplicity and reliability. It doesn't rely on moving parts or complex machinery which can wear out or fail over time. There are no moving parts, no complex machinery, just the elegant flow of electrons driven by a temperature difference. This solid-state nature of RTGs makes them incredibly durable and long-lasting. This makes RTGs incredibly reliable, perfect for missions where failure is not an option. In the harsh environments of space where maintenance is impossible, the reliability of RTGs is invaluable. The Seebeck effect, though discovered centuries ago, continues to power our exploration of the cosmos, a testament to the enduring power of fundamental physics. From the depths of space to the most remote corners of our solar system, RTGs have been a constant companion, providing the energy needed to explore and discover. While RTGs have proven their worth in space exploration, their reliance on highly radioactive isotopes like plutonium raises understandable concerns, especially for applications closer to home. But fear not, for a new generation of nuclear batteries is emerging. One that prioritizes safety and versatility: Betavoltaic batteries. Unlike RTGs, which utilize the heat from radioactive decay, Betavoltaic batteries directly harness the energy of beta particles electrons emitted during radioactive decay. These batteries employ less radioactive isotopes, significantly reducing the risks associated with handling and disposal. Betavoltaic batteries represent a paradigm shift in nuclear battery technology, focusing on safety and sustainability without compromising performance. Imagine a world powered by batteries that last for decades, eliminating the need for frequent replacements and reducing electronic waste. Betavoltaic batteries offer this possibility, paving the way for a future where energy is abundant and sustainable. Let's delve deeper into the inner workings of these fascinating power sources.